Hello. We continue our paragraph projection theorem and orthogonality, and now let's talk about orthogonality. Let us have some linear set A and closed. As we know, it is with such sets are called subspaces in H. Linear, of course, is convex, so projection theorem works here, and so for any element from H, there is a unique element from L, so linear sets are particular case of convex sets, so projection theorem also works here. So we can say what Xl is projection of X onto A, and first claim we like to say to prove about this projection is the fact what X minus its projection is orthogonal to L. What means what X minus PL X multiplied to Y is equal to 0 for each Y from L. Orthogonality means what inner product is equal to 0. Let's prove it. Let us have some real parameter, and let us consider such function of this parameter. We know what this element is closest to X in A, and Y is some arbitrary element from A. So this element is also some element from A. This function achieves its minimum if here we have closest element to X in A. So it's easy to see what minimum is achieved in with lambda equal to 0. Because in this case we have only this part. Let's memorize it and continue. If we simplify this relation, the square of norm is the inner product of element by itself. Here was minus. Next, using actuals, we can write so we have a quadratic function by lambda, and the minimum of quadratic function is achieved where derivative is equal to 0. Let's calculate derivative. It's not difficult to calculate the derivative of quadratic function. Here is a linear part, so derivative is equal to this, and here is a quadratic part. So we have this, and as this function achieves minimum if lambda equal to 0, so derivative in the point 0 should be equal to 0. And this derivative here, this term disappears, so we have only this one. And it should be equal to 0. So we have got what inner product of this difference is equal to 0 for each y from A. It's exactly what we like to prove. Next theorem, what we need, well, actually it's called lemma. Continuity of inner product. So if we have two sequences, xn would converge to x and yn would converge to y in H, then inner product of xn and yn converge to inner product of x and y. Proof. let's consider the absolute value of difference. If we subtract xn, inner product of xn and y, and then add, we can obtain these two terms, and we can evaluate as a sum of two summands. In both terms we apply Cauchy-Bunyakovsky-Schwarz inequality. Sequence X converges, so it's bounded. So we can estimate each element of the sequence by some constant. This term converges to 0, as yn converges to y. The same here. So both terms converge to 0, so the sum converge to 0. So indeed, if two sequences converge, then inner product converges as well. Let us have some subspace in H. Its orthogonal complement we will define as set of all, I don't know, x from y's from H as they are orthogonal to any element from A. So set of all elements what orthogonal to any element from A. Please prove yourself what this orthogonal complement is also subset in H. We will discuss it in our exercises. So, and two more definitions. We say what our space H, that x and y, two subsets of H. We say what H is decomposed into sum of x plus y and write this if for each h from our Hilbert space exists x from x and y from y, such what h is sum of x and y. So in this case we say what h is sum of x and y. And we say what h is decomposed into direct sum of x and y, and write this if for each h we can find unique x from x and y from y, such what h is sum of x and y. So if this representation unique, we say what h is decomposed into direct sum of x and y. And next and last theorem in this paragraph. Let H is Hilbert space. L is subspace in H, so closed and linear set. Then H can be decomposed into direct sum of L and its orthogonal complement, into direct sum of two subspaces. And second orthogonal complement, so orthogonal complement to orthogonal complement of L coincides with A. Let's prove it. Well, first let's prove what each element of H can be represented as a sum of elements from L and orthogonal complement. So each element from H, it can be presented as a sum of its projection into L plus H minus this projection. As we know, this is an element from A, and this element orthogonal to L we have proved it recently, so it is an element from orthogonal complement. So we have found two elements from L and orthogonal complement. Sum of this element is equal to H. So we already proved what H is presented as a sum of L and its orthogonal complement. Let's prove what this sum is direct. Let us assume that we have two representations. So H can be presented as M plus M orthogonal, one from L, another from orthogonal complement, and also it can be represented as sum of two other elements, L and L orthogonal. Let's move all elements from L into the left hand side and all elements from orthogonal complement into the right hand side. So we have M minus L is equal to L orthogonal minus M orthogonal. This is element from L. This element is all from orthogonal complement. So both elements belongs to both sets. So they both belong to both L and orthogonal complements. Because left hand side belong to L, right hand side belong to L orthogonal, but they are equal, so both sides belong to both sets. What does it mean? It means that each element is orthogonal to itself. For in particular L minus M is orthogonal by itself. As we know, according to fourth axiom of inner product, it happens only if element is zero. So M is equal to A, and similarly M orthogonal is equal to L orthogonal. So yes, this representation is unique, and we have direct sum. Let's prove what second orthogonal complement is equal to A. If we need to prove what two sets coincides, it's usually can be done as by provement of what these sets belong to this one and vice versa. So let X belongs to L, then X multiplied by Y is 0 for each Y from L orthogonal, according to definition of orthogonal complement. It means what X belongs to second orthogonal complement. So one implication is proved. Let's opposite X belongs to second orthogonal complement. According to first item, X can be represented as a sum of element from L and element from orthogonal complements, such that X is equal to sum of these elements. Let us prove or multiply everything to L orthogonal. X L orthogonal equal to L orthogonal plus L orthogonal by itself. So X is from L, this is from orthogonal complement, so it is 0. So sorry, X is from second orthogonal complement, so if we multiply it into element from the first orthogonal complement, it will give 0. The same here, L is from L, this is from L orthogonal. So third term is also equal to 0. So L orthogonal is 0. And here it is 0, so x is equal to L, what belongs to L. So we proved what x belongs to L, and now we prove opposite inclusion. So finally our second orthogonal complement coincides with L. That's all for this theorem and for this paragraph as well.